Hi, good day. So for today, we are going to talk about the paired samples t-test. Now, the paired samples t-test, also known as matched pair sample t-test or dependent samples t-test, is one of the ways on how we can find the significant difference between two different data or two different sets of variables that came from dependent samples. Now, paired samples t-test can only be used if the two data that we have are normally distributed, and therefore, paired samples t-test is a type of parametric test. Also, because in paired samples t-test, our data are normally distributed, then the most appropriate level of measurement that we should use here is under the interval or ratio scale. Now, to give you an example of a research where we can use the paired samples t-test, let's have here the effectiveness of X. Our product here is X. Effectiveness of X as a soil neutralizer. Now, for you to be able to prove that your product is an effective soil neutralizer, you actually set up 5 soil samples here. So we have here 5 soil samples labeled A, B, C, D, and E. We have here 5 different soil samples. Now, what we did here was we obtained the pH of these soil samples before the application of X, and we also obtained the pH of these same set of soil samples after the application of the product X. Okay, so the pH before the application of product X are 4, 6, 4.3, 5.1, and 6.8, and the pH after the application of soil neutralizer of our product as soil neutralizer are 7.1, 7.9, and so on and so forth. Now take note that these two data here, the pH before the application and the pH after the application, only came from one set of sample, this set of sample. Okay, and therefore, these samples are dependent samples. Okay, so our data here, the pH before and pH after, only came from one set of sample, these samples. Okay, so dependent samples. Now, right after we obtain the pH before and after, we also obtain the total for pH before and pH after. Now, there are some computations that we should do here before we proceed to the major computation itself. Okay, so first we need to determine the difference between the data for before and after. So that's like 4 minus 7.1, 6 minus 7.9, and so on and so forth. And we will have here this column for the difference. Now, D here stands for the difference between the before and after. So we have here negative 3.1 as the difference of 4 and 7.1. 6 minus 7.9 is negative 1.9, and so on and so forth. And then we also obtain the summation of these values, and we have here negative 12.5 as the total for the difference. Okay. Now, we are also required here to get the mean for the difference. Okay, so we are not going to get the mean for before or mean for after, but we are going to get the mean for the difference. So you already know how to get the mean of any values that we have. So we have here the mean for difference is equal to negative 12.5 divided by our sample size, which is 5. We have here 5 samples. So negative 12.5 divided by 5 is equal to negative 2.5. So the mean of this difference is negative 2.5. Okay. Also, we are required here to get the standard deviation for this difference. So again, we are not going to get the standard deviation for before or after, but we are going to get the standard deviation for the difference. And again, you already know how to get the standard deviation. So we have here the formula for standard deviation for difference, and that is square root of the summation of the mean for the difference. We already have this one, and that is negative 2.5 minus the individual D, or the individual differences that we have here, or the individual difference that we have here. So negative 3.1, negative 1.9, and so on and so forth. And then we are going to square our differences here, divided by n minus 1. N is our sample size, okay, which is 5 minus 1. Okay, so by plugging in all the data that we have here, so we have here standard deviation for difference is equal to square root of, for the first one, we have here again the mean difference the mean for difference is negative 2.5 minus the first data that we have here is negative 3.1. So minus negative 3.1, okay, square, plus the next value is again negative 2.5 minus the next value is negative 1.9, so minus negative 1.9 square, plus again negative 2.5 minus the next data which is negative 3.7 square, and so on and so forth. So we are going to do that in all data, in all individual data that we have here, okay, over our n, which is 5 minus 1. Now, by simplifying this equation, then we can have here standard deviation for the difference, and that is square root of 3.86. So we have here 3.86 as our numerator and 4 as our denominator. And by simplifying further this equation, then we can have here the standard deviation for the difference, and that is 0.98. Now, later on, we are going to use these two values here, the mean for the difference and the standard deviation for the difference, in the computation of the t-test proper. Now, the next things that we are going to do here are to determine the null hypothesis, the degrees of freedom, the alpha level or level of significance, the type of test, the critical value, and the decision rule. Now, for the first one, for null hypothesis, our null hypothesis here is there is no significant difference between the pH before the application of our product and the pH after the application of our product. That is, the pH before and the pH after are just the same. They are just equal. Now, for the degrees of freedom, we have here n minus 1. That is the formula for the degrees of freedom in paired samples t-test. Now, n here is our sample size. We have 5 samples in our research, and we have here 5 minus 1. Degrees of freedom is equal to 5 minus 1, and therefore our degrees of freedom here is 4. Now, for the alpha level, our alpha level or level of significance is always 0.05 or 5%, which means that we only allow 5% of the sample size to fall under the rejection region. Okay. Now, for the type of test, we have here two-tailed test, okay, because as we have noticed here in our null hypothesis, we have no direction in our null hypothesis. We did not use any comparative adjectives in our null hypothesis. We did not say pH before is greater than the pH after, or the pH before is less than the pH after. We did not use any comparative adjective. So we are not sure on what will happen to our research. So therefore, our type of test here is two-tailed test. Now, because our type of test here is two-tailed test, then what we did with our 5% is that we also divide this 5% into 2.5. So if we have here our normal distribution curve, we did not locate, or we did not just accumulate this 5% into just one part of this normal distribution curve, but rather we divided this 5% into 2. So 5 divided by 2 is 2.5. So the first 2.5 is actually located at the extreme left part of this normal distribution curve, so here, and the other 2.5% is actually located at the extreme right part of the of this normal distribution curve, and therefore we have here two rejection regions. So for example, if we compute our paired samples t-test value, and our value falls right here or right here, then we need to reject our null hypothesis. But if, for example, it falls right here or between this point and this point, then we need to accept our null hypothesis. Now, as we have noticed here, there is actually a clear distinction or a clear line that separates the rejection region and acceptance region. Like, if our value falls under here, then we need to accept our null hypothesis. If our value falls under here, then we need to reject our null hypothesis. Now, what is this clear line? What is the value of this clear line? Now, this clear line is this line here and line here is actually determined by our critical value. And for our critical value, we need to consult with our t-distribution table. Okay, now in our t-distribution table, there are actually 3 things that we need to know first. Okay, the degrees of freedom, the alpha level, and the type of test, which we already determined earlier. Okay, so let's take a look at our critical value table, or the t-distribution table. This is our critical value table for t-test. Here, we know that our type of test is two-tailed, our alpha level is 5% or 0.05, and our degrees of freedom is 4. By intersecting the value under 5% in two-tailed test and the value under 4 degrees of freedom, then we can say that our critical value or the T-crit is 2.776. So, knowing now our critical value, which is 2.776, then that means this line here, okay, is negative 2.776. And this line here is positive 2.776. Now, this one is negative because it is located at the left part of our normal distribution curve, while this one is positive because this one is located at the right part of our normal distribution curve. Now, with these two critical values, what will be our decision rule here? Our decision rule is that if the computed t or the tcom is less than or equal to negative 2.776 or greater than or equal to 2.776, then we need to reject our null hypothesis. Or in short, if our value or if the computed value falls under the rejection region, whether at this part or at this part, then we need to reject our null hypothesis. Now, let's proceed to the computation proper of the t-value for paired samples t-test. Now, the formula for the paired samples t-test is t is equal to the mean of the difference, which we already obtained earlier, divided by the standard deviation of the difference, which we already obtained earlier, and the square root of n, where n is actually the sample size. Now, by substituting the values that we already obtained or computed earlier, then we can have here t is equal to negative 2.5. So again, that is our mean for difference, negative 2.5. Okay. And we also have here the standard deviation for the difference. So 0.98, we substituted this value to here. Okay. And our sample size is 5, so square root of 5. Now, by simplifying further this equation, then we can have here t is equal to negative 2.5 divided by 0.4383. And by simplifying this equation, then we can have here t is equal to negative 5.70. So this is now our t computed or tcom. Okay. Now, for our analysis, our t computed is negative 5.70. Okay, while our critical t is negative 2.776 or positive 2.776. In this case, because my t computed is negative, then I am going to compare this negative tcom here to negative t-crit, okay, not to positive t-crit. So I am going to compare this negative 5.70 to negative 2.776, not here. Okay, and as we have noticed here, of course, negative t computed is less than the negative t-crit. Negative 2.776 is greater than negative 5.70. Okay, so this 5.70 is less than this one. Okay, now since negative tcom is less than the negative t-crit, so again, in our decision rule earlier, if the computed tcom is less than or equal to negative 2.776, so we know that negative 5.70 is less than negative 2.776, then we need to reject the null hypothesis. So with that, what will be now our conclusion here? Our conclusion here is that there is a significant difference between the pH before and pH after, because our null hypothesis here is there is no significant difference. We need to reject this one, and our conclusion now will be that there is a significant difference. Okay, so that is how we can use the paired samples t-test in computing the significant or in determining the significant difference of two different data that came from dependent samples.